In this video here, we're going to take a look at the projectile motion formulae. So to conclude this chapter here on projectiles, you need to be able to derive general formulae related to the motion of a particle that is projected from a point on a horizontal plane and moves freely under gravity. So before we actually take a look here at the derivation of the projectile motion formulae, let's just actually introduce the projectile motion formulae. So to introduce the projectile motion formulae here, let's say that we have a particle that's projected from a point on a horizontal plane with an initial velocity of u at an angle alpha above the horizontal, and this moves freely then under gravity. So there's four results here that you need to be familiar with. So for the first result then, this is for the time to reach the greatest height, and this is given then as u sine alpha over g. Now for the second result then, this is for the range on the horizontal plane, and this is given as u squared sine of 2 alpha over g. Moving on to the third result here then, which is for the time of flight. So for the time of flight then, this is given as 2u sine alpha over g. And now for the very last result here, this is for the equation of trajectory. So for the equation of trajectory here, this is given as y equals x tan alpha minus gx squared times by this fraction here of 1 plus tan squared alpha over 2u squared. Now before we take a look here at the derivation of these first two results here, what I am going to say almost as a warning here is basically don't try and remember these four results here. Okay, so these four results, right, they're not given in the formula book, and I would not recommend trying to learn and memorize these four results. Basically, if you have an exam style question or an exam question that wants you to use one of these results here, okay, so these are the four results that you need to be aware of. And like I said, if the question wants you to use one of these results here, the question would be structured in such a way. So for example, part A would ask you to derive one of these four results here, and then part B or part C, for example, would then want you to use the derived result. Okay, so that isn't to say that you can't use these results without, deriving them first, or, the question actually giving it to you. I wouldn't try and do it. Okay, it's very easy in an exam to, have a bit of a blank and misremember or just completely forget these results here. So don't rely on them. And I wouldn't say or wouldn't suggest trying to memorize these four results. Okay. So like I said then, for this video here, what we're going to do is show the derivation of these first two results here. So for the time to reach the greatest height and for the range on the horizontal plane. And then for the remaining two results here, we'll derive those in separate videos. So for the time of flight and for the equation of trajectory. Okay. So let's get started then on deriving these first two results here. So let's get started then with this question here. So for this question, we're told that a particle is projected from the point A on a horizontal plane with an initial velocity of u at an angle alpha above the horizontal and moves freely under gravity until it hits the plane at the point B. Given that the acceleration due to gravity is g, we want to show that for the first part here, part A, that the time of flight t can be expressed as t equals 2u sine alpha over g here. So for part A then, what I'm going to do here just to get me started is to draw a quick diagram. You don't have to, but I do find it helpful. So I've got the ground here, right? Like so. We've got this point here, A. So this is the point of projection. And we also have the initial velocity of u here. Okay. So we call that u meters per second here, like so. And then the projectile will move something like this here. Okay. Not perfect, but you get the idea. And it strikes the plane then at this point here, which they've labeled as B. Okay, point B there. So for the first part then, what we need to do here, well, it applies to both parts, right? We need to start by splitting this into components here. So let me do this. Let me do the horizontal component anyway in red. So that's for the horizontal component here. So for the horizontal component then, this is ux here, and ux then is equal to u cos alpha. Okay, so ux then is equal to u cos alpha. And now for the vertical component then, let's do this in blue. So for the vertical component here, right, that would be uy. And uy then is equal to u sine alpha. Okay, so we get u sine alpha there, like so. So what I'm going to start off with here then is by resolving vertically here then, I'm going to take upwards as positive. So resolving vertically here then, taking upwards as positive. So what do we know here then? Well, if you think about this, right? So the time of flight t, so we're going from this point here to this point here. So my vertical displacement, right, is equal to 0. There's no change there. We start at vertical point at this point here. And we also finish at the same point here, right? In terms of a vertical sense. So S, the displacement, is equal to 0. So for u then, the initial velocity here, right? That would be uy in the vertical sense. That's u sine alpha. So u then is equal to u sine alpha, like so. What else do we have here? We've got acceleration, right? So acceleration is acting downwards here due to gravity. That's g here. So in that case then, if gravity is going downwards here and we took upwards as positive, then a is equal to minus g. So just be careful for that, right? So a is equal to minus g. And then in that case here, t, the time of flight then, that's just capital T. Okay. So in that case then, based on what we have here, we're going to use, then S equals UT plus a half AT squared. Okay. Well, S is equal to 0. So 0 is equal to UT. So UT here then, I'm going to get U. I'll bring the T down in front of this as well. So I get UT sine alpha. Like so. So that's UT here. We then have a half AT squared. So plus a half. Oops, where's my pen gone? Try again. So plus a half AT squared. So A is minus G. So a half times minus G times capital T here. Like so. So in that case then, what I can do here, oops, that should be T squared. Apologies about that. So now what I can do here is factor out a T, right? So 0 is equal to, I get T lots then, of U sine alpha. Get U sine alpha here, like so, minus a half GT. Okay, because if I've got T squared here, we factor out the T out, we still get 1 remaining inside. So minus a half GT there. Okay. So if this is equal to 0 here, right, this equation is equal to 0, I'm going to get two solutions here. So my first solution is T equals 0. So I get T equals 0, right? And T equals 0 corresponds to the point A here. Okay, so that's the point A. So we'll make a note of that here, just so we don't cause any confusion. And then the second solution here is given as U sine alpha minus a half GT is equal to 0. Okay, so U sine alpha minus a half GT is equal to 0 here. Okay, so to solve this then, just add a half GT to both sides. We'll get half GT is equal to U sine alpha, like so. Obviously, what we're looking for here then, and this should be a capital T as opposed to a little t, just to be precise here. And I'll do the same here. So minus a half GT, same again here, like so. Now we want T equals 2U sine alpha over G. We're getting pretty close, right? So the first thing I can do then here is times 3 by 2. So I get GT is equal to 2U sine alpha. And then finally, right, it was want T here, just divide both sides by G. You could have done that all in one step, but just so I can show it clearly here, I'll do it all separately. So T is equal then to 2U sine alpha. Just move my pad here, it's in the way. So 2U sine alpha over G there. Okay. And there we have it. So as required then, we've derived the result in part A. So as required there, giving us the solution to part A. So now let's move on to part B then. So for part B here, it wants us to show that the range R here on the horizontal plane can be expressed as R equals U squared sine of 2 alpha all over G. So if we just think about this for a moment here, right? The range is the horizontal distance then from the point of projection to the point where it strikes the plane. So we're just going to label that here on my diagram, right? And that's the range here, which they've labeled as R. So I'll label that here on the diagram as well, like so. So for the range here then, what we need to do is just resolve horizontally here, right? If we're looking for the range, it would make sense just resolve horizontally here. So I'm going to resolve horizontally here, taken to the right as positive, like so. And because we know when we resolve horizontally here that the acceleration is equal to 0, we can simply use s equals vt here. We're going to use s equals vt. Okay. So in that case then, what is s here? Well, s represents the displacement. So the displacement here, right, is just the range, which we've labeled as r. So s is equal to r here. Now for v, this is just the horizontal component here, right? So that would be ux, which is equal to u cos alpha. I get u cos alpha. And then we times this by t here. So t in this case, right, for the range, is actually just the time of flight, which is capital T. So we get u cos alpha times by t here. And we know that t is equal to 2u sine alpha over g. We established that in part A, right? We showed how to derive that result. So we times this then by 2u. So we get 2u sine alpha all over g. Okay. So let's just multiply this together here. So I get 2u squared. I get 2u squared. I get sine alpha times cos alpha. So sine alpha, cos alpha here, like so. And then finally, this is all over g. Okay. And this is for the range here, r. Okay. Now, clearly, what we've got here isn't quite what we want. It's getting close, but we are still a little bit off here. But hopefully, you can kind of look at this right-hand side here to my equation and hopefully spot how we just manipulate this into the required form here. The way that we do this is by using the double angle formulae, right? We're going to use a double angle result then for sine here, because what I've actually got here is u squared times by 2 sine alpha cos alpha. So for part B then, we have 2 sine alpha cos alpha here. And this is equal to sine of 2 alpha. Okay, so sine of 2 alpha there, like so. So we can rewrite this then. What I've got here for r is r equals, we had 2u squared, but obviously this was u squared times 2 sine alpha cos alpha, which as we've just mentioned here, using the double angle formula for sine then, is sine of 2 alpha. So we've got u squared sine of 2 alpha, and that's all over g, exactly as we required. Okay, so as required there, and there we have it. So as required and proof complete. Okay, and there we have it. So as we mentioned then for this video here, we're only going to prove the derivation for these two results, right? The following results we will prove in separate videos. So if you're looking for those, I'll leave a link in the description down below. But there we have it. So that gives the solution there to this question here, question 1. And that brings the end then of this video here on projectile motion formulae.